Hi guys, welcome to our first video for the waves unit and the optics unit, and this is going to be all about wave characteristics and what different types of waves there are, as well as certain rules that all waves apply with. Now we're going to go in particular with a couple of specific types of waves in more detail, but we're going to worry about that later. This one is just characteristics that all waves have. Alright, so we start out with the different types of waves. Now, as you know, we hear the word wave pretty often, and most of the time, the first thing that people come to think of is water. There are other ways that you could think of it. You could also think of it using sound, or you could think of it using light, or you could think of it using people and different types of people waves. Now, there's also zombies. I mean, you could use waves to say like a wave of, in a video game, a wave of people coming that you have to attack. But in general, all of these waves have certain rules with them, and they all follow certain properties that we're going to talk about in this video. Now, sound and light are a little bit different, and light we're going to spend a whole separate unit on because it's very interesting, but we're going to go through what all of these have in common. So the definition of a wave is a continual disturbance, oscillation, or vibration that transfers energy from one location to another. In general, anything that's a wave is transferring one thing to another. So in terms of water, it's transferring water over. In terms of light, it's bringing light energy over. In terms of like video games, it's bringing a wave of people over. But either way, it's adding energy into something, and it doesn't really always have to do with mass. An oscillation is a repeating fluctuation in a physical object or quantity. What that's really telling you is it's like if something happens a repetitive motion over and over again. So for example, if a pendulum swings back and forth, an oscillation would be the one time it swings back and forth. So if there's a repetitive movement, it's the first time it does that repetitive movement. Now, one oscillation, a single one, is a pulse. So one turn back and forth of a pendulum would be an example of a pulse of a wave. It's one thing that happened that consistently repeats itself when we deal with waves. Now, there are different types of waves in the scientific vernacular. The first one is mechanical. A mechanical wave is something that must travel in a medium, so there must be some sort of physical mass or object or something for it to travel through. A big example here is water, because the water wave travels through water. Without any water, there's no wave. Another example is sound. You can't hear sound in space because there's no air molecules, because sound needs a medium. It needs some sort of molecule around for that vibration to occur. The other type of waves are electromagnetic waves. Now, electromagnetic waves have to do with the two fields, the electric field and the magnetic field, interacting with each other. The big example here is going to be light, but the other ones are X-rays, radio waves, cell phone waves. All of these types of waves are all waves that deal with the interaction between the electric and the magnetic fields. Then we get into more particular mechanical waves. There are two types. The first one is transverse. That's a wave in which the particles in the medium move perpendicular. So the example is water. So while water is moving forward, the wave itself moves up and down. So that's what it means when the medium is moving perpendicular to the motion of the wave. So we'll have this up and down motion going on in a water wave, which also will look like for people who have taken trig or are taking trig, like a sine or a cosine wave. Then there's longitudinal. That's a wave in which particles of the medium move parallel. So that big example of that is sound. When you say words, you're creating vibrations in the air that slowly go forward. Another example is if you push on a slinky really fast. The wave will look something like this, where you're going to have open spaces and then compressed spaces, and open spaces and compressed spaces, and that's causing this small vibration, which is what we hear using our ears. Then there's different characteristics of these waves. There's frequency, which is going to have a unit of hertz, which is going to be how often something happens. The examples are 5 per second. Period, which units is in seconds, which is how much time does it take one thing to occur or one to take past. Amplitude, which is in meters, which is how tall are the waves, or how hard are the waves, or how much energy is in the waves. Wavelength, which is in meters, which is going to be how long the wave is, or how much time it takes for a wave to occur, depending on the type of wave. All of these things are characteristics of all waves, and we're going to go more in depth to all of them in equations. But the last one, which is a big one, is speed. Speed is going to, of course, be how fast the wave is moving. And you can calculate it, and we're going to go through the calculations in this whole unit. Okay, so first let's go a little bit more in depth with wavelength or amplitude. Wavelength is the distance between consecutive corresponding points. And I'm going to do a bunch of overlapping with the idea of wavelength and amplitude because it's two of the most important things with a wave. So wavelength can be from crest to crest, which crests are up top, the top point and the top point, or trough to trough, which is the two bottom points, or it can be any point which is exactly the same. So for example, this is the top of a crest, and this is the top of another crest. Amplitude is the distance from the middle of the wave to the top of a crest or the bottom of a trough, which in this case would be up here, up to a crest, or if you want to do bottom, to a trough. Now what you notice is with waves, the distance of a crest to the middle and the trough to the middle will be the same. Then there's frequency and period. Alright, so frequency is the number of cycles completed in a period of time. So basically the number of times for something to happen within a certain amount of time. So I could, draw 5 things in 3 seconds, and that'd be my frequency. Units are hertz, which hertz is the same thing as saying 1 divided by seconds. Then there's the period, and period is the time it takes to complete one cycle. So they're sort of the opposite of each other. One thing, the frequency is asking you how many times something happens within an amount of time. The period asks how much time it takes for one thing to happen. Its units are in seconds, and there are two equations that connect each other. You can see that frequency is 1 over the period, and period is 1 over the frequency. So these things are inverses of each other. And we're going to go through how to calculate this stuff in class, but I think practice problems. So if a wave has a frequency of 5 hertz, how long does it take for one cycle? Well, if that's the case, we just do the reciprocal of 5 divided by 1, so 1 divided by 5, which is 0.2. Then there's if a period of a wave is 1 second, or 0.1 seconds, what is the frequency of the wave, or how many cycles have happened? Well, if the period of a wave is 1 second, then we do 1 over that, and that would give us 10 hertz. Then the relationship between period and frequency, well, those two things are inverse to each other. And we'll go through how to calculate this when we aren't just given frequency to find period in class. Oh. Okay, I'm going crazy. That's fine. Okay, we'll go through these 3 answers in class and see if we have any questions and use them as example problems. I had a boat on B. What would happen to it as the wave moves? Well, as it moves, it would probably drop. But to really make up some rules, we can remember that waves transfer energy without transferring mass. The particles in a transfer wave can only move up and down. So we can't say that it's going to move left and right. On longitudinal waves, they move right and left. And we'll go through this again in class. So we have particle A. Which way do you think it would move? Up or down? Well, the way we can tell this is the next part that's coming is going to be higher than where it was, so it's going to be moving up. So it goes from there to there. The way to check of it is which part of the wave is coming next, and if it's a crest, then the object's going to move up, and if it's a trough, then the object's going to move down. We'll spend more time on most of these concepts in class, but I want to make sure you have all these notes, because I will not be going through the definitions during class, and I will not go through the equations. Most likely I will just ask you what the equations are. If you have any questions, or if I went too fast, I suggest rewatching the video, and I hope you guys have a great day, or weekend, or night, depending on when you choose to watch this. So, bye!